In this video, I'm going to go through kind of what is expected for your lab report that's due tonight. So a couple of things that you'll want to have open as you work on this. You'll want to open up your Rower Derby Crash Lab report document. Okay, so that's a Google assignment on Canvas, and it should look like this. For part one, what you want to do is you want to copy and paste your data table and graph from the work that we did in class. Okay, so that was actually Maddie, sorry. I got to start with mine. The lab report wants me to start with mine. So I was the red boat. So I'm going to Control C and go over into my lab report and I'm going to Control V. I can paste it unlinked and paste it in there. Okay. If you want to adjust the formatting and make it look nicer, you can. I'm not going to grade you on that. I'm just fine if you just copy and paste it in. So then you're going to do the same thing for your graph. Control C and then paste it in there. Okay, so some movie magic. I have my data tables and my graphs pasted in here for both myself and my partner. Okay, if you go to part one, that now if you have completed part one, you've copy and pasted your both the graphs from part one and data tables into the lab report document. Okay, so now you are setting up kind of a separate problem here in part two. Okay, so here we are in part two. And basically what you need to do in part two is solve a problem very much like what we did at the beginning of class yesterday, where we spent quite a bit of time looking at Fred and Dora, the swimmers in class. And so if you look at the instructions, you're going to use the velocities you discovered in part one, so those constant average velocities that you calculated in the spreadsheet, to predict the crash location of the two rowers. Okay, so you and your partner, let's say you're rowing straight towards each other, and predict where they're going to meet or crash. Okay, in order to make your prediction, you need to write an algebraic equation for each rower's position as a function of time. Okay, so what that essentially means is similar to what we did yesterday. We're going to make an equation for each of our rowers in the form of position as a function of time. The x naught is the initial position of the rower. And this equation only works if you're traveling at a constant velocity. So that will be the constant velocity of the rower. Okay, so from the data that I have copy and pasted into my lab report document, I can see that the average velocity of the yellow boat in this case was 6.4, and the average velocity of the red boat was 3.5. Okay. In this problem, they're traveling at each other, and I've asked you to set up the reference frame, if you read the instruction, with 500 meters being where the yellow boat is, and 0 meters being where the red boat started. So what that means is that this yellow boat is traveling in the negative direction. Okay, so that is kind of your setup. So you're going to have to figure out a position as a function of time for the yellow boat, okay, and a position as a function of time for the red boat, okay, using the velocity and initial position. Okay, and same thing for, let's do for our red boat. Well, that's more red. Okay, so for our red boat, our initial position and our velocity here. Okay, so hopefully that was helpful for part two. That's what I'm looking for you to do. And then very much like what we did yesterday, you need to figure out, okay, what is going to be true when these two boats crash. Okay, how can I figure out at what time and what position they crash? Okay, and I'm telling you that you can get a good start by writing an equation for the position as a function of time for each of your boats.